Just think about everything you do online. Buying something, hopping on a video call, working on a shared document, it's all a nonstop digital conversation, right? But have you ever really stopped to think about what the true cost of that conversation is? Well, it turns out the theory that built our entire digital world was, let's say, due for a major upgrade. Today, we're going to dive into the work of one scientist who gave us a whole new language to understand it all.
And look, this is not some small adjustment we're talking about. When a giant in computer science like Avi Witterson says something is a beautiful and rich and complex extension of the most foundational theory of information, you know you're looking at a full-blown revolution. And he's talking about the work of one guy who's changing, well, pretty much everything. And that person at the center of it all is Mark Braverman. He's a computer scientist over at Princeton, and for more than a decade, he's been meticulously building this incredible new framework to describe the very nature of information itself.
And yeah, the world has definitely taken notice. In 2022, Braverman won the IMU Abacus Medal. Now, to put that in perspective for you, this is basically the highest honor you can get in computer science if you're under 40. It's only given out once every 4 years, so it really recognizes work that is truly game-changing. So what exactly did he do to earn it?
Well, to really get his breakthrough, you first have to understand him. And his story isn't just about crunching numbers. It's about translation. It's all about how a childhood spent moving between countries and cultures shaped a mind that could just as easily move between totally different scientific fields. I mean, his journey was just incredible. By the time he was a teenager, Mark Braverman had lived in 3 different countries and spoke 3 different languages. He was born in Russia, then his family moved to Israel after the Soviet Union fell, and then later they moved to Canada. That is a whole lifetime of change and adaptation packed into just your childhood years. And that experience gave him this really unique way of seeing the world. As he puts it, he became a natural translator, not just of languages, but of big ideas. And this skill, this ability to bridge different worlds, that became the signature of his entire scientific career. And you could see this unique approach really early on. When he was still a 17-year-old graduate student, and yep, you heard that right, 17, he decided to tackle a problem from a completely different field. It was a challenge that went against the core beliefs of all the top researchers, a move that was seen as, well, kind of heretical. And he was asking this huge, fundamental question. Are there problems out there that aren't just really, really hard to solve, but are actually impossible to compute? Like, no matter how powerful your computer is or how much time you have, you just can't. His test case for this question? Something called Julia sets. They're these absolutely beautiful, mind-bendingly complex mathematical objects. They're fractals, which means they have these infinite, intricate patterns that just go on forever. So what happened was this fascinating clash of scientific cultures. You had the experts in dynamical systems, the people who studied Julia sets, and their intuition told them that, sure, some of these are hard, but they're all computable eventually. But Braverman, bringing that outsider's, translator's perspective from computer science, proved that they were wrong. He showed mathematically that for some of these fractals, computing them wasn't just hard, it was literally impossible. The result was a total shockwave. His collaborator on the project even called it a mathematical miracle. It just completely shattered the deeply held beliefs of an entire field. And it was exactly this kind of fearless, boundary-crossing thinking that he was going to bring to his next, even bigger challenge.
Okay, so let's get to the work that actually won him that Abacus Medal. He turned his attention from the beautiful, abstract world of fractals to something we all deal with every day: digital communication. He decided it was time to update a core theory that had been the standard for almost 80 years. And that original theory came from the legendary Claude Shannon. Back in 1948, this guy basically wrote the rulebook for the digital age. He's the one who gave us the bit as the fundamental unit of information, and he built the entire mathematical framework for understanding one-way communication, like a radio broadcast or a signal over a noisy phone line. But right there, that's the key. Shannon's theory was designed for a one-way street. The internet, though, it's more like a chaotic, 6-lane roundabout with traffic going everywhere. It's all about interaction, a constant back and forth. The old model just wasn't built for the world we live in now. So this led Braverman to a really crucial question. How do you mathematically measure the cost of an actual conversation? Not just sending a single message from point A to point B, but that whole interactive dance that happens when people or computers are trying to get something done together online. His answer was to build a whole new theory from the ground up.
He created a new language, a new way of thinking called information complexity, and it's designed specifically to measure our modern digital conversations.
So, what is it? Well, at its core, information complexity is a precise way to measure how much information has to be revealed when two parties are communicating back and forth to complete some kind of task. It's not just about sending data, it's about sharing and changing that data to achieve a goal together.
Let's make it super simple. Imagine you and a friend each have a secret list of animals. Your goal is to figure out which animals appear on both of your lists just by sending messages back and forth. Information complexity doesn't just count the number of bits you send. It actually measures the absolute minimum amount of information you must exchange to solve that specific problem. It's the true information cost.
And that right there, that's the big paradigm shift Braverman introduced. Figuring out the animals you have in common, that's not just sending data. It is a computational task that the two of you are solving together. And when you think about it, every online purchase, every collaborative Google Doc, it's all computation, not just simple transmission.
So why does all this matter to you and me? Well, this new language helps us understand the true cost of, well, everything we do online. It opens up new doors for developing way smarter data compression, for creating much more secure ways to communicate, and it even helps us understand the absolute fundamental limits of what computation can achieve. It's huge.
So you develop a whole new theory of information. You win one of the highest honors in your field. What do you do next? For Braverman, it seems the focus is shifting from solving the problems himself to inspiring the next generation to do the same. And this is the man behind it all, the translator who connected different worlds of science to give us a brand new language. A language that helps describe the digital world that every single one of us lives in.
You know, he doesn't see that Abacus Medal as just an award for past work. He sees it as a new responsibility. He actually calls himself an ambassador now, and he's on a mission to encourage students to chase after those bold, maybe even crazy ideas. The very same kind of ideas that might seem heretical at first.
And we'll end on this really powerful thought from Braverman himself. He says that in fields like his, the next huge revolution isn't always decades of work away. It could be just around the corner, hidden in a new way of thinking, a new language. A breakthrough could be just one translated idea, one crazy question, away from being solved.